All right, so we're gonna keep talking about damping, but now we're gonna look at the, let me see if I put a number for viscous damping. Number, so now we're gonna do one that is known as Coulomb, just the same guy as in electrical engineering, but this one is also known as dry friction damping. Okay, so the above damping is caused by the friction between the rubbing surfaces, that's it. So basically, is the one you have seen in statics. It's just the friction between, let's say, the table and this marker, no? This one is not Coulomb damping or dry friction. Okay, so in that case, the damping force is equal to the friction coefficient, and you have learned that stuff, times N. Okay, and obviously the damping force would be opposite to the motion. And in this equation, you probably recognize N is the normal force. Okay, so basically to find the equation of motion, it's very simple. So let's do the example we always do here. So you have a block. Of mass M attached to a spring. And this will be sliding on a surface. Let's say it will be, okay, this will be the spring K, mass M. And let's say the origin of our reference frame is right by the CG of the block. Okay, so in order to find the equation of motion, we need to do to follow some steps. The step number one is always to do the free body diagram. So what will be the free body diagram in this case? Remember, we need to do two. This one. And this one here. So let's see, what would be the forces being applied to this block over here? You probably might have here gravity, normal force. I mean, this is like we did on the previous notes. Then assume that we move this one, displace it a bit to the right. So then the spring is going to create a force to the left. Force of the spring would be equal to what? Kx. And if we move this one to the right and assume some friction over here on the surface, So the friction force will oppose the motion, which is to the right. So it means that the friction force will go to the left. Okay, and we know that the friction force should be equal proportional to mu n. Okay, on the right hand side, we do the kinematics effects. So it's moving to the right. So we know here we'll have MA, which by now we know is the same thing as mx double dot. So what can we do over here? So this would be step 1, free body diagram. Step 2 is to write down Newton's equation. So what type of motion is this object going to have? Just translation. So what is the Newton equation that is defined translation? Is summation of forces equals to MA. And remember that here on top, I do 2 free body diagrams because this one is related to the one other forces. So this one related to this one, and MA is related to this one, no? Okay? So let's see. Here, we also need to define a reference frame. So I had here X. So let me do X and Y from the CG. So if we do, to save some time, let me first do summation of forces on the Y direction. It will give you this. Is it any motion on the Y direction? This is only moving on the X. So that means that this will be 0 here. So this will give you what? From the figure, will give you N minus mg equal to 0, or will give you that the value of the normal force is equal to mg. All right, next we can do summation of forces on the X direction. So again, all these equations come from the free body diagram. So on the X, what are we going to have? Minus kx minus mu sub n. I don't see anything else on the X direction. And this will be equal to, so now I look on the figure on the right hand side, mx double dot. Okay, so over here now you see that n is equal to mg, so we can substitute. So this will be equal to what? Minus kx minus mu mg equal to mx double dot, which will be equal to mx double dot plus kx equal to minus mu mg. Or if you want, we can have here x double dot plus k over m x equal to minus mu g. And again, you recognize that this is of the form x double dot plus omega n square x equal to minus mu mg. Where basically omega n would just be equal to the square root of k over m. And by now you should know that that is the natural frequency of vibration, no? Okay, so again, you see that you always get to this type of equations. What's different from the previous one is that this time the right-hand side is not zero, so that means that it's not homogeneous. So that is not homogeneous, but you can make it homogeneous, all right? All right, so that's it. I mean, you see it's pretty simple. Okay, and the last type of damping that I'm going to mention, and that one is a lot more complicated. That's why Jan is not covered, but I want to mention it, is the hysteresis friction. And that one is more related to the material of the system of your block than to any external factor. So 23. So hysteresis damping. Okay, so let me try to give a quick explanation here. Is that when materials are deformed, energy is absorbed and dissipated by the material. This effect is due to friction between the internal planes which slip or slide as the deformation takes place. Okay, so basically means that if you think about an object that is deforming, and let's say you have like a thing about plywood. Plywood is made of different layers, no? Okay, during the deformation, the different layers are going to rub against each other, all right? Even though it's just the same material. The different layers are going to rub against each other. So if you want, it will be Coulomb damping between each one of them. So you're going to lose energy, no? Okay, throughout the deformation. Or imagine you glue two pieces together. When you start deforming and bending, those two pieces, you're going to create shear at the location, no? Okay, so that deformation creates some type of, creates like, if you want, Coulomb damping or dry friction, but this is internally within the structure, all right? So if you look at the structure, what's happening is this. If we do a figure where you have the stress, so generally here you will put the strain. So the strain is related to what? To the deformation. What is strain? Elongation by initial length. So it's related to the deformation. And here you will put stress. That is related to what? To the force. So generally what happened is that it's not exactly like that. but it will create some type of loop. So imagine you have a block that is vibrating. Now imagine I bend it like that, I let it go, so it's gonna start vibrating like this, no? Okay, so if I let it go, let's say, so this will be loading, and this will be, if you want, unloading. So if we're able to trace the variation of the deformation with the force, it will create some type of cycle. Okay, so I have here, I'm not gonna do it, but basically you can see that throughout this phase over here, some energy is going to be dissipated, okay? So it's gonna create some damping within the internal structure, okay? All right, so I have a full derivation about showing what is this proportional to, but since really we're not gonna cover this much in this course, all right? I'm going to skip it. I think the other thing you need to know is that there's some type of damping that is also within the structure. Okay? And this is called hysteresis damping, and that's it. All right. So now we're going to go starting to learn how to solve the differential equation of motion. So remember, so far we had that the equation of motion, we always look under the form x double dot plus omega sub n squared times x equal to 0, no? Okay? So how do you solve that equation? All right, so let's find here now. Solution. To the undamped free vibration equation of motion. So let's over here so far, comma, it was observed that the single degree of freedom equation of motion of an undamped system, and let me just add over here homogeneous, is of the form so basically if we're dealing with just translation, we had x double dot plus omega sub n square x equal to 0. Or if it was rotation, we had theta double dot plus, if you want to call, you can call it omega sub n, but I like to call it omega sub theta because to show its rotation, theta equal to 0. Okay, so what we need to do is to find what is the general solution for this type of equation. Okay, so next one, let us find the general solution of the above differential equation of motion. So these are the differential equations. Okay, so here, this is always the same procedure. So first, I'm not going to specify the procedure at the beginning, but I will do a summary at the end. All right, so let's say we take the differential equation, x double dot plus omega sum n squared x equal to 0. So this is the equation we need to solve. So this is important now because this is something we're going to be doing the rest of the semester about this class. So step number 1, we're going to assume harmonic solution. So basically, every time you solve a differential equation, what do? You assume the solution, and then by the end, you need to find what are the constants in front of that assume functions that should be the solution of the equation, and you need to determine those constants. So what does harmonic mean? Harmonic just means that the solution is going to be some type of combination of sines and cosines. Okay? What is harmonic? Sines, cosines that just follow some type of period and so on. So over here, really, you don't have to assume the one I'm going to do now, but it works out good because of the sign. So in this case, the assumed harmonic solution, you're going to assume x of t is equal to a constant or a series of constants that we'll have to determine, and then e minus lambda t. And you will see what is lambda, okay? Let's say later. Here's something that you always get confused and you think you're doing it wrong. It doesn't matter if you assume minus or plus lambda t. It does not matter mathematically, okay? What happened is that with the sign, it works out better if you put minus, okay? And once we have damping, the solution would be minus I, like the complex number, lambda t, but you can also take lambda positive lambda I t. So it does not matter if you put plus or minus over here, okay? It does not matter. It will work out fine. So you assume the harmonic solution. So we have the harmonic solution. What would be x dot equal to? This will be equal to what? Minus lambda c exponential minus lambda t. What would be the second derivative? X double dot will be equal to what? Lambda square c exponential of minus lambda t. All right? So step number 1, assume harmonic solution. You can take plus or minus. It does not matter, okay? 2, what do you think we're going to do? We're going to substitute these solutions into the differential equation. So substitute harmonic solution. Do I need to write down? So you substitute this solution into differential equation. So substitute harmonic solution. I'll just do it for the first time. Into differential equation. So then what do you have? You have x double dot plus omega n square x equal to 0. So this will give you what? Lambda squared. The x double dot is lambda squared c exponential of minus lambda t. And then we're going to have plus omega n squared, and x is just c exponential minus lambda t, and this will be equal to 0. All right, so now it's just basic algebra. What can we factor by? We can factor by c exponential minus lambda t. And what do we have? Lambda squared plus omega n squared equal to 0. So basically, this equation here is equivalent to this one over here, no? All right, we just substituted we say we assume the harmonic solution, we substitute, so this is the new form of this equation. Now, when is this equation satisfied? So we're gonna have two cases. Either one is the solution when this side is equal to 0, when will be this side equal to 0? When c is equal to 0, no? Yeah? And then what will be the other solution? When this term in the bracket will be equal to 0, okay? So let's say the above equation is satisfied if and only if, and this from now on, generally I summarize it like this, E and 2Fs, okay? A little bit faster. So case 1 is when C, okay, I'm gonna put it here, C, really to be detailed, this term is equal to 0. This will give you the trivial solution. So basically it just means 0 equal to 0. So first case. Second case, when lambda squared plus omega n squared equal to 0. Which means what? That lambda squared must be equal to minus omega n squared or that means that lambda will be equal to what? Plus, minus, I hope you know that, I complex notation, omega sub n, where you all know that I squared should be equal to minus 1 in complex notation, no? So this is complex number. Okay, and that's why the reason you're going to see on the next step, that's why they put here a negative value. Okay, otherwise, I mean, you will see on the next step, it will be the algebra will be a little bit different. Okay, so now let's go back over here. So we have lambda is equal to I omega n. Okay, where do we have lambdas over here? Over here, no? Yeah, so that means that we can have two different lambdas. All right, so that means okay, so that means that the assumed solution, which is x of t, we assume was equal to c exponential of minus lambda t. And now, what did we just solve on the previous page? We know that lambda is going to be equal to plus minus I omega sub n. So this means that x of t is going to be of the form of what? C1 exponential. Let's first take the negative value minus I omega sub mt. I put the same one, the first one over here. Let's say the negative one plus C2 exponential of the positive I omega sub mt. All right, did you see what I did here on this step? The only thing I do is I take the assumed solution, the assumed harmonic solution, and I plug those two values, no? If I plug those two values, that means we're gonna have two constants. All right, so now just algebra. So now we can say by using or recalling Euler's equation, you're going to see that this is the same thing as writing down sines and cosines. So what were the Euler equation? E of I, let's say, of theta of a complex number. This is equal to what? Cosine theta plus I sine theta. And E to the minus I theta is the same thing, cosine theta, but minus I sine theta. Okay, so this sign over here means, like on the computer, enter. I'm not going to write down everything. Next thing I'm doing, I think it's pretty obvious. I'm going to substitute this notation. I'm going to use the Euler equation to rewrite the above equation. All right, so we're going to get, so if you want, let's write it down. So using Euler's equation to rewrite x of t, what are we going to get? X of t will be equal to what? C1 of cosine omega nt minus I sine omega nt plus C2 cosine omega nt plus I sine omega nt Okay, we can just rewrite this as let's say it will be C1 plus C2 cosine omega nt plus I of C2 minus C1 sine omega nt. Or I could just write this as x of t is equal to A cosine omega nt plus B sine omega nt where A will be equal to C1 plus C2 and B will be equal to I C2 minus C1. Okay, so at the end, remember I told you that to do the harmonic solution is to assume that the solution is in function of cosines and sines, no? Which is basically what we have over here. All right. So now the constants A and B, or if you want C1, C2, will depend on what? So the general form of the solution, the same thing we say that the general form of the equation will be of this form. The general form of the solution will be of this form. Okay. And the constants A and B will depend, if you want, on the initial condition of our system. So for example, you could say, let's see, do I have a figure here? Okay, let's say, obviously, the vibration of this is not going to be the same if initially I pull it, let's say, instead of 1 meter, I pull it 5 meters. That would be one initial condition, no? Okay, because it will be different. You agree? All right. Then the other thing could be what? Let's say you can just let go from a velocity of 0, or you can define that right at the time when you're going to let it go, you can maybe push it with a certain velocity. All right. But that velocity can be different. So depending on those two types of initial conditions, boundary conditions, if you want initial conditions, you're going to determine different values for A and B. But the form of the solution will always be the same. So let me just write that down. Okay, and the last step over here will be to determine. So last step on the procedure should be determine the constants A and B. So now these two constants necessitate two, I think it's only one S, two initial conditions to be determined. Okay, but we do that in an example a bit later. Okay. Hope I'm not run out of paper. Okay, so this is the more traditional way of the equation of the solution of the equation of motion, or the differential equation of motions, okay? But to understand better the properties of the solution, we're gonna write it down a little bit different. Okay, so let us write the solution x of t of the SDOF equation of motion under a different form to better understand its properties or characteristics, okay, more than properties. Okay, so our initial equation is x of t equal to a cosine omega and t plus b sine omega and t. Okay, so this is the equation. The equation can be written as x of t equals to amplitude a and p. And now it doesn't matter, you can actually use sine or cosine, but here I'm going to use sine for omega and t minus phi. But again, you could use here cosine, it will not change anything, okay? So we're going to write under this form. Where the amplitude which is the amplitude will be equal to what? A squared plus b squared, and we take the square root. So it should be the amplitude of, I will do a figure in a little bit. This will be the amplitude of the deformation. And phi is known as the phase angle which will be equal to minus tangent, so inverse or minus, so find the angle of the inverse tangent of A over B. Okay, I'm going to do a quick proof. You don't have to trust me. So proof. Let's say consider A equal to minus amplitude of sine of the phase angle phi, and B would just be the same thing but in positive, and will be the amplitude sorry, of cosine of phi. So if you had selected here cosine, what would you have? A will be the same thing with the cosine, and B will be the same thing with the sine, okay? We'll not change anything. But let's go and substitute, okay? Let's see what we'll get over here. So substitute into, so x of t, but which form? So obviously we're trying to prove, so we're going to substitute into this form, A cosine omega and t plus B sine omega and t. So this will give you what? X of t will be equal to minus amplitude of sine phi cosine omega t plus amp cos phi sine omega and t. Okay, and now this is very simple if you know that equation, obviously, but using, otherwise it's very complicated, but using the trigonometric relation of sine of two values u minus v is equal to sine u cos v minus cos u sine v, okay, from that trigonometric relation. So obviously here you can factor out, I mean, do I need to do it? You can factor out by the amp over here. Right, let's do it if you want. Let's factor out by amp. I'm going to run out of space. That's the only problem. If I factor by the amp, what am I going to have? I'm going to have cosine phi sine omega t minus sine phi cosine omega t So you see, I should actually factor out by the minus amp, would be better, but more clear. This will give you what? X of t, because what's the relation? Is sine. Yeah, it works, that's good. You see, this would be sine, so what is u? For us would be omega and t, and it will be phi, no? Okay, so it will give us amplitude of sine of omega and t minus phi as we were expecting. Or if you want, we can say as prescribed. Okay, so let's keep looking now. Let's look at this part of the derivation. All right. So over here, I'm running out of paper, but hopefully we'll have enough. okay, where the amplitude, so in this equation here, is equal to a squared plus b squared. That's what we said over here, no? Yep. So let me take the square root then. Let's take the square root, but it's going to become area notation. So we're going to have here. All right, so what is A? A, we have them over here, no? It's these two values. So the first one will be amp square sine square of phi plus amp square of cosine square of phi square root. So here you can see right away that this would be equal to what? Amp square of cosine square phi plus sine square phi and what is cosine square plus sine square? 1. So you see right away at the end that we're going to have amplitude equal to amplitude, no? Because of the square root. So basically we prove that the amplitude is a squared plus b squared. So check. And the last thing we need to check is what? The one of the phase angle, okay, which is right here. So the phase angle, we're going to have phi is equal to minus tangent minus 1 of A over B. So this is what we need to prove. So let me just do A over B. Again, will be equal to what? We have the two expressions over here, so it's straightforward. But minus amplitude sine phi divided by amplitude cos phi. You can see right away that's going to give what? Minus tangent of phi. Okay? If you solve this equation, what do you get? Phi will be equal to the tangent minus 1 of A over B, no? So again, as expected. Okay, so why are we doing all this stuff? So all this stuff is just for the really, that deviation is not that important. Important thing is the figure. So let's say this is x of t, the solution. And we need to plot it in function of time. Here. Maybe a little bit more. This will be t. I might not be that good plotting it, but Okay, so you do some type of sine or cosine function here. You see, I don't do it starting from 0. There's a reason. Okay, and at the same time, I'm going to do another figure right under. Which is just a circle, a trigonometric circle. Okay. So let's see, let me come here to a figure. Let me move this in case the ink is gonna go through. Okay, so I want to show a couple of things here. First one, what is the difference between the sine and the cosine? The cosine function, what is cosine of 0? It's 1. So the cosine function starts something like this, no? Okay, and the sine function, sine of 0 is 0, so basically it starts this way, all right? But basically, sine of cosine have exactly the same shape. The only thing is that they start at a different point, correct? So if we move this point to this location, then everything is the same, correct? You can rewrite the cosine as a sine, or you could rewrite the sine as a cosine, correct? So when we have this assumed solution at the here, what is this minus sign doing here? He said, okay, if our solution here, the sign, you can leave it untouched, but we know that the cosine function, we can write it as the sine function if we just move it to a certain point. All right? All right. Now, I'm going to use the same figure. You agree with me? Let's do it with the cosine. I think it's easier. The cosine function is the same thing as going around the circle. All right? Cosine of 0 is 1. Correct? What would be cosine of pi over 2? 0. No? So it goes, or if you want, okay, it goes here. Maybe then you go to this point, but maybe here with the, I mean, it works, but maybe it doesn't look like the right direction. Let's go to move to this one, okay? Let's go to the sine. If we look at here, sine of 0 is 0, no? So from here, it goes up. Now from here to here, it goes down over here, no? From here to here will be this part over here, and from here to here will be this part over here, correct? And then we start the same thing all over again. All right? Okay? So basically what I'm trying to say over here is that by having a phi over here, we were able to rewrite the cosine in function of the sine. Okay? But that means that we need to face our solution a little bit to the right or maybe a little bit to the left from the 0. Okay? So that value over here that phase is generally equal to phi, I mean, not generally equal, it's equal to phi over omega m, because that depends on how fast you are moving around. All right, in this figure, the height between this point and this point, this is easy, which should be what? the amplitude, and then it doesn't matter if we start from this point to this point or from this point to this point. Let me do it from this point to this point. This will be equivalent to just one full turn around the circle. Okay, so this will be one cycle, which means one turn around the circle. So one turn around the circle is how many radians? Is 2 pi radians, and it's going to do that in, and I'll tell you, omega n pi. So omega n will be the vibration, no? You can go faster, you go around, and pi will be the period. So basically, is so times, so tau, here is the period. And this should be in seconds. So basically, this time is going to tell you how fast this is going around the circle. And let me just redo here the same figure, I mean, almost identical figure. It's the same one that I did on the piece of paper. All right, so it would be x of t. Let's say this will be t. So here, this is the angle phi. What does it mean? Is that if we start from here, before we get to 0, we're going to reach a point over here, no? Okay, so if you want, here you have the first part of the solution. Let's see. It's not going to look good, but this will be phi over here. No, this angle. All right. And now from here, we'll have just the normal solution for the sine. All right. So again, I don't know if you want, we can put the same information here, from here to here, but you could do from here to here. Again, this will be one cycle, which means that it's doing 360 degrees or 2 pi radians in omega n pi. So basically, if you don't remember this one, you don't need to remember, but what would be the units for omega n? Omega n units are radians per second, no? So the units of 2 pi should be radians, correct? So you need to multiply by a variable, which basically is the frequency, how fast you go around this, which will be the period. All right, so let's say here point P. All right, let's put here point P here. And let me just write down the last thing I just mentioned. So let's look here at this figure. Let's see how I can write this down. So point P makes one complete revolution. So it goes all around the circle, which I call a cycle or one cycle, okay? During the time required by the angle to increase basically, I'm just writing what I have on top. Increase to increase by 2 pi. Okay, so the time required to increase to pi is known as the period. And is defined as, so the period equals to, 2 pi over omega sub m. So we know that 2 pi, this would be 2 pi's units are radians. Omega sub n units will be radians per seconds. And tau should be seconds. Okay, one last thing, sorry guys. And the frequency, okay, which the units will be hertz, which 1 hertz is what? 1 over second, will be equal to what? F basically would just be 1 over the period, or should be the inverse of the top one, no? And this should be page 28. All right, so that will be the end for today.